go. And let's see, our first presenter is Eric and the Crosswave. So Eric, I'll let you introduce yourself and introduce your project. Let's see if I bring it up here. Wonders of modern technology. If you click on enough things, it will.
All right, my name is Eric LaClair. I am a senior in the Bachelor of Science Electrical Engineering Technology program here at Vermont Technical College. My project is the Frostwave. Like it sounds, it is a reverse microwave. Instead of heating food, it is supposed to cool food down or liquid. Before I begin, I'd like to give special thanks to Barry Woodworth, who I don't see here today, but Barry was very instrumental in helping me complete my project. I decided to go with a 3D printed case for the Frostwave, and I never used either SolidWorks or the 3D printer, so Barry was very helpful in getting my design created and printed. Also Professor Michael Marceau helping me select the right parts, and also Kevin Orth for ordering those parts and getting them up here from the Randolph campus. Okay, so my top level description, the Frostwave. So an infrared sensor will be mounted to the top of a small enclosure facing down. Small computer fans will be mounted on the sides and back of the enclosure. The front of the enclosure will be open. When the infrared sensor detects a temperature that is greater than the preset temperature programmed into the microcontroller will send a digital output to a solid-state relay that switches on all 6 mounted fans in the enclosure. Once the infrared sensor detects a temperature below the preset threshold, the microcontroller will switch the solid-state relay off and the fan will stop. The sensor will detect the temperature of food and drink. Basically, the sensor will detect the temperature of food and drink, switch the fans on until it has cooled, then automatically shut off. And there are some problems with that already that I'll get to shortly. So this is my Gantt chart, my schedule. The schedule was constantly changing week to week. I was never actually able to really adhere to the schedule I initially created at the beginning of the semester. But real quick, in the beginning, I selected and ordered parts. Once those arrived, I tested some code, especially for the IR sensor, and make sure that could communicate with the Arduino. I based my project off the Arduino Uno, basically because it's pretty reliable and easy to use microcontroller. Then I had winter break. After break, I ordered additional parts, finished my code for it in Arduino. Designed and built the solid-state relay circuit, which is pretty straightforward. Had spring break, and then after break, I got down to designing the 3D printed chassis and started printing that, which actually took a little while to get right. I don't have pictures of the lid that we tried to do. It is in the other lab, so you'll be able to see what it came out with. But you'll see the 3D case actually came out pretty well. And then the final couple of days, I just tested and refined the code for it. So here's my bar napkin drawing, the Frostwave. Initially, I wanted to have some kind of either radiator fans, like you see in the back of an AC unit, or like on a fridge, you'd have a coolant or a pressurized gas flowing through the radiator fans, and have fans blowing across that, or blowing air across that into the enclosure there. You see I have food down there. So it get blasted with really, really cold air. So it basically be sort of like a refrigerator or an AC. Up on the top, you have the IR sensor, and in the brain, all the electronics, the microcontroller, whatnot. And then on the right there, you see my hand-drawn fan, sort of, that's the walls of the enclosure that the fans are actually mounted to. This is what I drew for Barry, so he could implement that in SolidWorks. Worked that pretty well. Here's my final circuit design. I have the Arduino in the middle there. On the side, you see the infrared sensor all the way to the right, and then the OLED screen. I picked those parts because they're designed for the Arduino, so it made it really easy to communicate with the microcontroller with those, and they also share the same inputs, the SCL and the SDA, and also 5 volts from the Arduino plus the ground, so that's all shared. So yeah, from the sensor and the screen goes into the analog 4 and 5 pins of the Arduino. I have a separate 9-volt power source for the Arduino, so it can be powered instead of USB. And then from pin 10 on the Arduino, the digital out of pin 10 goes into the solid state relay, which is connected to a 12-volt power supply. All the fans are wired in parallel, so they're all share the same voltage. Real quick, the solid state relay, it just takes the input and then switches on. There's an optocoupler inside, so it's completely isolated. I picked that because the fans, computer case fans, have a lot of noise on them, so this is completely isolated from the microcontroller. So once the relay gets that signal from the Arduino, then it connects this circuit on the other side, which allows the 12 volts to go to the computer fans. And I also have, I threw in some LEDs there to let you know if something is hot or cold. You'll see pictures of that. Those are just connected to pin 8 and pin 7, which are also digital outputs, which you'll see in code. So here are snippets of the Arduino code. I just have the main parts of it. These two floats right here, object temp and ambient temp. That's really how those sensors and the LCD screen kind of communicate with the Arduino using this MLX dot read object temp and read ambient temp. On the other side, you see I set the pin modes for pin 10, 8, and 7, selecting them as outputs. And then pin 10, that's for the solid state relay. And then pin 8 and 7 are for the LEDs. And basically, the code is just an if-else statement. If object temp, which is what's read from the sensor, that's greater than or equal to 110 degrees Fahrenheit, it will send the input to the solid state relay to switch it on. And as soon as the sensor detects the temperature lower than that, it'll switch the solid state relay off and the fans will go off. Here are my pictures of the 3D printed case and lid. That's the SolidWorks file that gets converted into a G file, which is uploaded to the printer. That's the finished product with the holes already drilled. Barry helped me. Barry drilled the holes for me while I supervised. And I've been told that that's actually the nicest thing that the 3D printer has produced in a number of years. If you look at the lid's got, for some reason, the lid was a lot simpler, but that we tried it twice and that got warped both times. Like I said, those are in the other lab, so you can look at those up close if you want. And the next picture is with the 6 fans mounted to it. And then here we have, since the lid wasn't working with the 3D printer, we opted for sheet metal, which Barry helped me bend the sides there, and he also drilled the mounting hole for the IR sensor. So that's the FrostWave complete without all the electronics. And then here we have the Arduino and then the breadboard. I didn't do a printed circuit board because I didn't think I had enough time, but next time I would definitely combine all of that into one neat, clean printed circuit board. That's a blue LED that's being shown. Ooh. Okay, so here's the final product. Here's the top of it with the breadboard and the screen and the microcontroller. You can see the solid state relay back there. And then I have all the fans wired in parallel on the other breadboard. And then this is like an inside view. And then here's the final product with, that's can't really see it, but that's Stouffer's French bread pizza, which was used extensively for testing. And then on the other side, you can see it's displaying the temperature. It's about 117 degrees, so it has a little bit ways to go. And the LED light is on. I picked these fans because they have a blue LED, and I thought I'd kind of convey that idea that it's cooling things. So my bill of materials, two of the things, the sensor and the screen were Arduino based, so that's why I basically picked those. They're also pretty cheap. The sensor was $15 and the display was $11. A lot of this stuff we actually had on hand, which is handy. The Arduino, I picked that because it was available. I had actually 2 of them, so that's why I picked that. The fans, I picked 8 of these fans originally. I only used 6. And I picked them because they have a hydraulic bearing in them, which is a lot quieter than your traditional bearing inside. They also are capable of being controlled by PWM, but I didn't actually use that feature. I didn't have time to really dive into that. 3D printed case was actually pretty cheap. It was less than $12. And the sheet metal and the hardware, it's hard to like really gauge how much that was, because with hardware, you have, you buy them by the hundreds, all those little screws and nuts, washers. And then I ended up using 3 variable power supplies for a specific reason I could explain later. But overall, it was only $240, which was below the, I think, $600 budget. So it came in well under budget. Could have really gone wild with that. But. Okay, so limitations. Does it work? Yes, yes and no. The circuit and the code work exactly as I designed them. The sensor detects a temperature. It compares that temperature to the pre-programmed threshold, and it'll send the signal to the solid state relay, which will switch on the fans, and it can do that all day without any issue. However, the second law of thermodynamics states that entropy always increases. So when food is heated, the molecules inside the food are in excited state or high entropy. And as you know, we cannot reduce entropy. A system in a higher state of entropy will tend to stay in that state. So what happens is this causes the fans to kind of turn on and off rapidly as the food bounces up and down a process at set threshold temperature. The way I could have mitigated that was designing a hysteresis gap in the Arduino, which is possible, but I didn't have enough time to really flesh that out. So I kind of went the easy road and just increased the delay for when the fans turn off. So the fans stay on a couple more seconds after that threshold is met. If you'll see in the demonstrations that the food the heat kind of returns once the fans go off. So it kind of takes a little bit longer. The fans come on again for a little bit, then shut off and come on. But they're not constantly switching on and off. So that's mitigated a little bit. So next time I'd choose a smaller microcontroller. The Arduino Uno is great, but it's way more power than I really needed. All I really needed, I think, were the SCL and SDA inputs, which a lot of their microcontrollers have. So I could have used like the Micro Mini, I think. And I would have designed and built a PCB and a small enclosure for it just to make it look nicer. And I would have used more robust hysteresis gap and maybe played around with the fan speed a little bit. My idea was taking the temperature from the sensor and then applying a certain PWM signal to increase the fan speed. Depending on if it's hot, it'd be higher fan speed. Questions? Let's go ahead.
We're going to have a demonstration. Actually, we have pizza coming, so
Yeah, hopefully the pizza will stay hot enough so that you'll actually be able to. Thank you.
all right. Thanks, Eric.